It's going to upset some people. All right, today we're going to talk about aliasing, which of course leads to anti-aliasing. I feel like you made me write anti-aliasing. Aliasing. Specifically, it's called aliasing distortion, but we always refer to it in as just aliasing. Again, yeah, most people are probably familiar with the concept of aliasing from anti-aliasing that you see a lot in your graphic settings for games. It's the same concept, right? It's preventing the same, so the aliasing they talk about in games is two-dimensional aliasing, which is the exact same concept that we're going to see here. It's just we're doing it in one dimension. But the stuff is the same. The techniques for getting rid of the same anti-aliasing algorithms work in one dimension as they do in two dimensions. So we're going to kind of take the scenic route to get there, though, because, you know, that's fun. All right, what did we talk about last time? Last time we talked about this concept of sampling, and more specifically, we defined this sampling function, right? This S of t, this continuous time sampling function. And we said that we got some continuous time sampled function that was just equal to multiplying the original continuous time signal times our sample function. Now, when we take all of that into the frequency domain by applying the Fourier transform, we're going to get some stuff. So we'll say that S, so the Fourier transform of our sampling function is S of j omega is equal to this, 2 pi over t times the summation from negative infinity to positive infinity of this train of delta functions. So delta of omega minus k times omega s, where, importantly, that omega sub s, is the sampling frequency.
Is there any reason why you wrote omega differently? And like normally write as like a W when you're like dealing with complex numbers?
So the honest answer is because the textbook switched over suddenly. And I think it's because we're going to kind of make the distinction. We're gonna look at these values as kind of like static values, rather than like when we write like a sinusoid, like sine of omega t, right? Has kind of a slightly different meaning, but it's at the end of the day, it's omega is omega.
Yeah.
Is omega, so it's all good. And omega s is equal to 2 pi over t, so 2 pi over the sampling period. Now from that, and from the fact that x of s is equal to x sub c times our sampling function, remember that our x sub s of t is equal to the summation, the bilateral sequence, x sub c of nt and delta of t minus nt, right? This is the equation that we got last time. Which means, and this is the important one, if we take the Fourier transform of this guy, x sub s of j omega is equal to 1 over t, k equals minus infinity to positive infinity of just this, x sub c of j times omega minus k omega s, and we cap it all off. So don't get too freaked out about this we'll never really have to deal with it by hand, but we wanted to state it just because it's going to kind of lead to what we're going to observe. Basically, just what it means is that when we take the Fourier transform of our original signal, our sampled signal is just going to be shifted around based on this minus k omega sub s. And it's going to look kind of like this. Let's say that we have an axis. We're going to do a bunch of drawing here. In the frequency domain, so we'll say that's omega. I'm going to call that point 0. And let's just say that our x sub c, our original signal in the frequency domain, just kind of looks like this. Where it tapers off its sum and hits back to 0 at what we call omega sub n and minus omega sub n. And this is our x sub c of j omega. This is the Fourier transform of whatever our original signal was. Now,
You changed omega again.
oh, I did, didn't I?
Omega.
That one I just did by habit. It's supposed to be the other one. Now we're going to plot our sample, or the Fourier transform of our sample sequence, S of j omega. And it's going to look like this. Let me use a different color. So that's 0. We'll have that. Actually, it'll be a piece out here, right? It's that train of impulse functions that goes forever. This is our S of j omega. Which means that when we get the sampled signal that comes out the end, in the frequency domain, let me put here, this is going to be, that point is omega sub s. This one will be 2 omega sub s. So these are all the sampling frequencies. So minus omega sub s, minus 2 omega sub s, and so on. Let's see, 0. I'm going to make a note here that we had those sampling points there and there in line with the graph above it. And let's see, we went out 2. Happens is the signal just gets duplicated at every point where there was an impulse function in our sample sequence. This is our x sub s of j omega. Okay, does that kind of make sense? So what happens is, if we then turn around and change, well, hold on. our sampling frequency. Let's do a new plot. Zero. Let's say now that I'm going to do my omega sub s every, I don't know, every third. So I'll do it here. So I've shrunk down my sample frequency. I've made it smaller. It's going to look like that. Here's our new S of j omega. Maybe that's why we should have stayed away from it. Just go back to the old omega. But we've come this far. All right. So what's going to happen now is probably easy to guess, right? Get that. We got 0. We get all of our signals again repeated like so. Just like that. So there's our new X sub s j omega. And notice that, yeah, we've got some overlap here, right? We have these regions where they actually overlap with each other. Oop, I screwed that one up. That one should go to there and there. Like that. These regions of overlap that's our aliasing. When the frequency domain signals start to crash into each other and start to mess each other up, that's aliasing distortion. Now, the relationship that has to hold to prevent aliasing this relationship has to hold, right? The difference between omega sub s and omega sub n, right? This is our sampling frequency. And omega sub n, if I scroll back up here, right? Omega sub n is the largest frequency that our signal extends out to. So you can think of it as the highest frequency present in the signal. So the highest frequency in x sub c of t. So the difference has to be less than or equal to omega sub n again. All right. Now, with a little bit of algebra, we get this in a form that we're probably a little bit more familiar with, that you may have seen before, which says that the sampling frequency must be greater than or equal to 2 times omega sub n This is called the Shannon Nyquist. Excuse me, the Nyquist Shannon theorem. It says that your sampling frequency must be greater than or equal to twice the highest frequency present in your original signal. Otherwise, you're going to get some aliasing. Bad stuff is going to happen. Your signal will become distorted. Let's dig into that just a little bit more and take a look at how that distortion kind of matters to us, right? Because this is still kind of a theoretical construct, right? We can draw the graph and be like, yeah, the graph obviously shows that stuff gets jacked up, but how does that lead us to actual distortion in our signal? And to get there, first what we're going to do is kind of draw our diagram, draw our model for our system here. You know, we're sort of continuing to refine our model for that ideal continuous to discrete converter. So we have our original signal coming in. It's being multiplied by S sub t, getting our sampled one, and then we're going to pass it through what we're going to denote right now as h sub r of t, or excuse me, little h. Yeah. And we're going to get left with what we're going to call x sub r of t. Now, some of this stuff is the same as what we've just seen, but we're going to go ahead and draw it again anyway. So, boom, 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 boom. So let's say that we start with the same signal, same frequency content that we had before. We'll call that 0. Make it a little bit smaller. So omega n minus omega n. That's our continuous time signal. Basically the same one that we saw before. From there, we know that we're going to get a sampled signal . That's going to kind of look like this, depending on what our sampling frequency is. That's our omega s right there. That's our 2 omega s. That's our minus omega s. That's our minus 2 omega s. So what's going to happen? We've chosen a sampling frequency that's big enough that we're not going to get any of that distortion. And then the last thing that happens is this h sub r of t is going to be a low-pass filter. And it's going to draw like this. So that's our h sub r of j omega. That's our cutoff frequency. Omega c minus omega c That's our low-pass filter. And it caps off at 1. So that's what our low-pass filter looks like, right? We're just drawing a box around the low-frequency stuff. We're going to multiply by that, so we're going to keep just the low-frequency stuff. So which means if we take, let's see, what was this? This was our x sub s of t, or x sub s of j omega, excuse me. Right, we multiply it by our h sub r of j omega, again, because we're convolving, right, which is multiplication in the frequency domain. That means that we're going to, well, let me say that. I don't want to take that for granted. So, coming back up to this drawing, right, we had, which is a different color, right, x sub t got multiplied by s sub t to give us this sample thing, x sub s sub t, right? It's going to get passed through this block, h sub r sub t, to get us x sub r sub t. And that means that x sub r sub t is equal to x sub s sub t convolved with h sub r sub t. Which means that in the frequency domain, x sub r of j omega is s sub s of j omega times h sub r of j omega. I just realized why the book switched over to the other omega. Because we're working all this out in continuous time. And it's making the distinction between the sort of Fourier transform of a continuous time thing. So this would be, radians per second, since we're technically talking about continuous time stuff. But all the math is going to work out the same. Okay, so all that to say that our x sub r is going to be the multiplication in the frequency domain. So we're going to take that signal and multiply it by that signal, and that's going to get us why? I want to know why. Thought we were friends. Means that low pass filter is going to filter everything out. All of the rest of the stuff gets filtered out by the low pass filter, and we're left with just this guy. So this is our x sub r of j omega. So to kind of recap that, going back up to our, well, I'll leave that down here. Our original process is we take our signal, we multiply it by our sample function, and then so that's going to create that train of our original signal sort of connected to the impulse train, and then we're going to hit it with that low pass filter to get back just the original signal that we had. So this is the guy that's going to become our x sub n eventually, right? So we managed to recover that original signal. Any questions about that?
Wouldn't it be a bandpass filter? Because I thought low pass filters would only filter out like one side.
Hey, that's a good question. So no, it is a low pass filter because it's centered around 0. Everything is symmetric around 0. So technically, this is higher frequency going out. Yeah, in practice, we kind of ignore the left-hand side here. And if you were to draw your vertical axis right there at 0, then you would see, well, we're just going out from 0 to omega c. Something like a bandpass filter would look like this. It would be a thing out here, 2, 3, and it's like complement over here.
Okay.
That's what a bandpass filter would look like in this kind of a graph. Okay. I know this stuff is super exciting, man. All right. So to bring it all back together, let's kind of work out a general-ish kind of example to show how aliasing can kind of jack up our recovered signal, the signal that we actually get as our discrete time signal. Let's say that we have a sinusoid. Suppose a sinusoid is the signal that we want to recover, right? We're going to say our original signal is x sub c of t is equal to cosine of omega naught t. All right, and the Fourier transform of that guy, x sub c, j omega, go to the Fourier transform table, you're going to find that it's pi times delta of omega minus omega naught plus pi times delta of omega plus, omega naught. So if we go to graph this, we're just going to see two little impulses. Call that 0. We'll say that, I'm going to draw them as different colors just to make it a little bit more obvious. We'll say the green one here is the one that's at omega naught. And we'll say the orange one is at minus omega naught. So that's our omega c, x sub c of j omega. So that's our original signal. So we just basically just a sinusoid coming in. This of course would be something like a radio wave or something. Would look an awful lot like this. The next thing we're going to do is apply our sample function to this guy. As I fight with one node for a minute. Let's see, 0. Okay. Now, let's say that we're going to do the samples at 3 ticks here. So that means our train is going to look like this. 2, 3. All right, this is our S of j omega. Now, if, this is the case, hold on, let me label that, omega s, 2 omega s, 3 omega s, minus omega s, minus 2 omega s, minus 3 omega s. So if omega naught here is, let's just say is 2, since it's 2 ticks out from 0, and omega sub s is equal to 3, since we're drawing it 3 ticks out from 0, are we going to get aliasing or not? What do y'all think? Concur. Edward says yes. Someone else says yes. Yeah, right. Because if we go back, remember our Nyquist Shannon theorem says to avoid aliasing, the sampling frequency must be greater than or equal to 2 times the omega sub n, the sort of largest frequency in the signal. In this case, our largest frequency is omega naught, which is 2, and our sampling frequency is 3, which is not greater than or equal to 2 omega naught. So since omega s is not greater than or equal to 2 omega naught, we expect aliasing. Okay, so let's set it up and see what we got. So first off, we would design we need our low pass filter. Let's go real quick and define our filter. Just like that. Let's say this is 0. And since our omega naught is 2 ticks out, we'll go like 2.5 ticks out. So 1, 2. We'll say that's our H sub r of j omega. All right, so we've got our sample points that are 3 ticks each out from 0. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And of course our 0 tick. We've got our filter, which is 2.5 ticks out. We'll go ahead and throw that on right now. Well, actually, take it back. Let's do that last. We've got our original signal that is each 2 ticks out from the thing. So I'll draw the green lines first. So all like that. So each green line is 2 ticks to the right of the sample point. The blue lines are all going to be 2. Ooh, I'm going to change these to blue since I got my colors mixed up. We'll draw that as blue. Will all be 2 ticks to the left. So you can see we get a whole bunch of garbage in our signal. So when we apply our low pass filter, that should recover our original signal. Well, what do we get? We get all this extra garbage sitting inside. Zero. So if this is our recovered x sub r of j omega, we can see that it does not look like our original signal. We have additional frequency count. We have a whole nother sinusoid in there. And in fact, it turns out that what you get is x bar of t is going to be equal to cosine of omega s minus omega naught times t, or cosine of all of that times t. So the sampling frequency makes its way into our signal, and the difference is what we get left over. So that was a long roundabout way of saying that when you're taking your samples, your sampling frequency has to be larger than twice, or less than or equal to, or greater than or equal to, excuse me, twice the largest frequency present in our signal. Any questions about that? Edward asks, if we're limited with our sampling rate, is there a way of doing additional processing with the aliased wave to arrive at the original signal, or would that require knowing the frequency of the original signal, which is what we're looking for in the first place, right? Yeah, so there are anti-aliasing techniques that let you kind of get away with this, but it does require knowing some things about your original signal. So if you knew what your signals were already, you could kind of mess around and play with it. So such as, we can sort of think of one right now, couldn't we? Like what would, instead of, if we knew that what our sampling frequency was, and we knew what our input frequencies are going to be, is there a way that we could have designed our system to avoid aliasing? How would we do it? We already kind of talked about it a little bit.
Without manipulating sample frequency.
Without, yeah, if we couldn't change the sample frequency, what else could we change?
Sample rate.
Not the sample rate, that's the same thing, it's the sample frequency.
Omega naught.
Can't change omega naught. Omega naught, that's the frequency of the signal. So we can't change the frequency of the incoming signal, and we can't change our sampling frequency. There is one other thing we can change.
The filter.
The filter, right? So instead of doing a low pass filter, in this case, instead of doing a low pass filter, what can we do? Well, we definitely don't want to do a high pass filter, right? Because a high pass filter is going to get all of that stuff. But you said it, right? Yeah, we want to do a bandpass filter, right? If we could design a specific bandpass filter, right? That was like just, so if we knew ahead in advance what stuff we were going to be working with, what our sampling rate was, and what our incoming frequencies were going to be, then yeah, we could create a bandpass filter to lock that guy in. Now, would this work for, this works in this case since we have very clearly defined sinusoids. Would it work for this guy? No, right, because we have that frequency content that kind of stretches out from 0 to some frequency. So it doesn't always work. But yeah, that is a very simple example of something we could do to achieve anti-aliasing. Just use a bandpass filter or centered around the frequencies that we know that we're going to be looking for. So, any other questions? Cool. Well, in that case, that is all I've got for you guys today. Thank you so much. I know that wasn't like the most riveting stuff in the entire universe, but it's important, and we're going to take it to some cool places. So, thank you so much. Have a good weekend. Be safe. I'll see you guys on Monday.
Have you found a Python project for next week?
Not yet.
Okay.
It's on my to-do list for the weekend.
What did y'all do for the resistor value for the last problem of the exam the other day? Oh, you're wrong.
Electronics 2.
What'd you get? I got the wrong answer.
I forgot to do the Wiggler loop.
I'm either making a big mistake or a good choice trying to take modern radar circuits next semester
Instead of
principles of communication systems, because I looked at it and talked a lot about.
Wait, you can take radar without taking Pringon?
Well, the thing is, I was talking to Maddox, and she said that I'm taking theory, and since I'm close to graduating, she's like, yeah, if you're close to graduating.